We are Team 22052, Popcorn Processor. Our team consists of Noah Miller, Team Lead and Mechanical Engineer, Robert Cardenas, Mechanical Engineer, Ella Spagnuolo, Biosystems Engineer, Juan Correa, Electrical and Computer Engineer, and Solomon Gollum, Procurement Lead and Industrial Engineer. Our mentor is Scott Wright. Our project sponsor is Thomas Ploss from Tucson Village Farm. Tucson Village Farm is an education-based farm for youth located in Tucson, Arizona. Tucson Village Farm offers youth programs that teach children about nutrition and healthy living. And one of the ways they do this is by providing children with popcorn, which is grown, washed, and dried on the farm.
The problem that Tucson Village Farm faces is that firstly the washing process is done by hand in a variety of water basins, and that process is quite slow. As well as the kernels are dried open air on tabletops, and not only is there limited table space, but the process is also time consuming and serves as a bottleneck. In addition to this, during this drying period, the kernels are vulnerable to birds and dust.
So our objectives for this project is to create a system that can wash and dry the popcorn kernels while at the same time it being educational and autonomous.
I'm going to go over some of the major system requirements. The first is that the system should be able to operate manually, along with the system being able to operate as an automated system. So the system should also be able to protect the kernels during use so that the crop is protected from pests and other outside elements. The system needs to be interactive for youth and users. The system is to also reduce the amount of time and effort to cleaning the popcorn crop. The system needs to be safe for youth and also include emergency shutoffs. And kernels also need to be able to be cleaned to an acceptable level and be dried so that they can be stored.
Popcorn processor will be powered by electric motors. Both the washer and dryer will be operated by two of the same motor, which have the same set of wires, including a high-speed wire, low-speed wire, a common collector wire. The brown and the yellow wires connect to the capacitor. The plug on the end of each motor is formed by the low-speed wire, the common collector wire, and the grounding wires. The plug is then connected to a 20-amp variable transformer, otherwise known as a variac. Once powered on, the variac will supply voltage to the motors, which also supplies user input, in which the user can set voltage levels that can change the moving speed of the motor. To ensure safety against electrical shocks, small plastic insulators will cover any conductive material by a crimp. Additionally, an emergency shutoff switch has been installed for both motors. Activating the switch will halt any power from entering the system. The 120-volt power supply of the farm will be the source of the power for the variacs. The plugs of the variacs will then be connected to a GFCI cable box, where it may halt power supply if a short were to occur within the system. This box would then be connected to the main power supply of the farm.
To better understand the philosophy that led us to our final design, these were the key points that dictated those features. The closed washer and dryer system served as the basis for the functions and the interactivity we envisioned of the washer and dryer subsystems. They each accomplish a main goal and they require minimal interaction for operation. The preliminary filter was inspired by a birdseed filter that was found on the internet. It was chosen to be included within the system as it would alleviate some of the burden on the washer and hopefully lead to a better quality kernel. In addition to this, the filter includes a window into the structure so it can serve as a demonstration or enrichment opportunity. So washer and dryer were required to have not only an automated motor-driven operation, but also a manual operation. This would again allow for the subsystems to be an effective demonstration for students and users, while also using the automatic modality to optimize processing efficiency. Initially, focus was placed on the dryer as our first critical design element. This was determined not only due to the devotion of two subsystems to washing, but also because drying was quickly determined to be the most time-consuming aspect of the process. The dryer was our first critical design element, and our initial goal was to optimize drying time to maximize production. This was originally envisioned as the kernels within a drum that would not only spin dry, but they would also have hot air blown across them. However, research was brought to our attention that eliminated this possibility for our design. Popcorn kernels actually will become damaged when dried in forced heated air applications, especially when the air is heated to above 120 degrees Fahrenheit. After this, the dryer design was now dictated by both balancing the optimal safety conditions for the kernels, as well as the speed at which the process could be completed. In addition to this, our initial moisture percentage goal of 10% was found to be somewhat extreme, as kernels can actually be reliably and safely stored at a relative moisture of 13.5%. The design analysis from our prototyping data demonstrated that a spin dry with blown cold air would be the best method to use for our dryer.
So going into research for the washer, we decided to kind of base our system off about the level of cleaning that the farm currently strives for and what they expect. And so the full washing process, we decided then to split it up into two parts, a preliminary dry filter, and then the wet washer, which will spin the kernels with water in a drum. That'll get excess chaff and dirt off. So from there, our research began as researching inspiration and possibilities for how to power the drum by a motor and be able to have the bike power it. And this was kind of point of our sponsor, really wanted the youth to be able to pedal a bike and have a drum spin. So we decided to include that in the washer. And as for removing chaff from the kernels, the foundation of this is that the chaff floats and the kernels do not. So when the kernels are agitated, chaff is able to float to the surface of the water where it can be skinned off the top with a strainer and disposed of.
Prototyping for Critical Design Element 1, the dryer, proved valuable in the analysis of the dryer design. The dryer drum was mounted vertically on a handheld drill and air was blown across it by a hairdryer at constant distances. The prototyping used three configurations: a simple spin dry control, a spin dry with blown cold or ambient air, and a spin dry with heated air. The moisture contents were measured every minute for 5 minutes for each method. This data would go on to create an analysis model for the dryer. The prototyping demonstrated mainly that the spin dry was insufficient and time-consuming for our design. It also clearly demonstrated that a heated air dry would lead to a faster drying time. Despite the fact that the warmer air will lead to a shorter drying time, the addition of heated air could greatly compromise the kernels after drying. The analysis also demonstrated that with blown ambient air, the drying time is not that much longer and the results would be far more safe and reliable. The drying time was estimated to be between 5 to 15 minutes per 5-pound load of popcorn kernels.
For some of the major documents that were created to aid our verification of the system, we have the verification data table, verification procedures, and the data sheets. So this is where we kept track of all our system requirements and where we recorded whether they were passed or failed when we did verification testing, and data sheets for parts of the system that needed to be analyzed to be sure that we pass these requirements.
The objectives completed, the system as a washer and dryer works marvelously along with the filter, where it also met all the safety requirements. Furthermore, the automation function works on the dryer. We effectively overcame any obstacles and incorporated changes when needed. We still have 7 more tasks to be completed and delivered to our sponsors.
The project introduced us to the industry review and design process, as well as serving as one of our first real-world applications of critical problem-solving and collaborative design. It has taught us the useful skills of procurement, scheduling, and delegation. Classes served as our first foray into engineering as an economic application of science and technology. A special thanks to the University of Arizona, our mentors, Heather and Scott, and Tom Ploss. On behalf of the team, thank you so much.